Somewhere, far beyond the reach of any telescope you could ever look through, drifts something unbelievable, a star made of diamond. Yes, you read that right. Not a metaphor. Not an exaggeration. Floating alone in the frozen silence of space is a star that's literally a colossal gemstone, a crystallized ball of carbon so massive it dwarfs imagination. This isn't fiction. Astronomers have actually found stars like this. The most famous one is about 50 light-years away, tucked inside the constellation Centaurus. It's technically what we call a white dwarf, the collapsed core left behind after a sun-like star exhausts its fuel and dies. But this particular remnant isn't just a glowing ember of gas. Its heart has hardened into crystal. In simpler words, it's a star-sized diamond. Its official name is BPM 37093, though scientists prefer to call it something much friendlier, Lucy, after the Beatles' song Lucy in the Sky with Diamonds. So how does a cosmic jewel like Lucy even exist? When a star similar to our Sun runs out of hydrogen to burn, it swells into a red giant, shedding its outer layers into space. What's left behind is the dense core, a white dwarf. These remnants are scorching hot and incredibly compact. Over billions of years, they slowly cool, and the carbon deep within them begins to crystallize under the crushing pressure, the same way diamonds form inside Earth, but on a scale no jeweler could ever comprehend. Except Lucy isn't a gem you could ever wear. She's roughly the size of our planet but weighs as much as our entire Sun. Imagine an Earth-sized sphere made entirely of carbon crystal, solid, dense, and heavy beyond reason. Scientists estimate Lucy's diamond heart would weigh around 10 billion trillion carats, that's a 1 followed by 34 zeros. If mining it were possible, which it absolutely isn't, you'd be richer than every civilization in the universe combined. But Lucy isn't alone in her sparkle. In 2011, astronomers discovered something even stranger, a planet made of diamond. Orbiting a pulsar, a kind of hyperdense neutron star, this world is believed to be the carbon core of a long-dead star stripped bare by its violent companion. The planet is about 5 times the size of Earth, and it whips around its pulsar once every 2 hours. Imagine that, a planet of diamond racing around a dead sun at blinding speed. Now, you might be wondering, how can we possibly know that these objects are made of diamond? It's not like anyone can fly out there with a pickaxe and grab a sample. The answer lies in the mathematics of light and vibration. As white dwarfs cool, they don't do so silently. They shiver. Tiny oscillations ripple through them, starquakes, scientists call them, and by studying those vibrations, astronomers can infer what's happening deep inside. It's like how geologists use earthquakes to understand the layers of Earth. In Lucy's case, the vibration patterns perfectly match what we'd expect if much of the star's interior had solidified into crystal. Since white dwarfs are composed mostly of carbon and oxygen, the result is a lattice of carbon crystal, a diamond heart forged by physics and time. And here's the cosmic twist, our own Sun will one day follow the same path. Roughly 5 to 7 billion years from now, after it swells into a red giant and sheds its outer layers, it too will cool into a white dwarf. Then, after eons of slow cooling, the carbon inside will begin to crystallize. Someday, long after Earth and everything we know are gone, the Sun will rest in space as a silent diamond corpse, the glittering ghost of a once golden star. Picture that. The Sun that gave us life, frozen solid into a jewel, glowing faintly against the eternal dark. It's poetic, in a way, stars that once burned bright eventually turning to diamond, their brilliance captured forever in crystal. But it also challenges our idea of what stars even are. We grow up imagining them as raging furnaces of fire and plasma, not silent, crystallized relics humming faintly with leftover heat. Lucy no longer burns. She shines softly with the residual warmth of her past life, cooling ever so slowly. One day, she'll go dark entirely, becoming what astronomers call a black dwarf, the ultimate fate of a white dwarf that has cooled beyond all glow. But the universe isn't old enough for black dwarfs to exist yet. That stage lies trillions of years in the future. So for now, these diamond stars drift in silence, dense, luminous, eternal. Some even pulse gently as they cool, ringing through the void like planet-sized bells. Those vibrations, measured across light years, have their own science, astroseismology, the study of starquakes. It's through this cosmic music that astronomers confirmed Lucy's crystallization, a blend of physics, harmony, and time itself. And Lucy isn't rare. In fact, it's estimated that up to 90% of stars in our galaxy will eventually end up like her, crystallized white dwarfs glittering invisibly in the dark. That means billions of hidden diamonds scattered through the Milky Way, each the tombstone of a dead sun. If future civilizations ever figure out how to mine them, assuming they can somehow extract material from a corpse star with the gravity of a sun, they'd have access to riches beyond imagination. Unlikely, yes, but not impossible. The idea of colossal diamonds adrift in space sounds like science fiction, but it's real astrophysics, one of many reminders that the universe doesn't need our permission to be absurdly beautiful. For centuries ago, astronomers thought stars were made of divine fire or celestial light. None would have imagined a sky filled with crystallized suns. And yet, here they are, stars that lived, burned, and died, leaving behind diamonds that shimmer quietly in the cosmic dark. It's tragic, and gorgeous, and deeply human, to know that even in death, stars leave behind something precious. A planet that's hotter than its star. Space runs on rules. Big stars burn hot, small ones burn cool. Planets, by comparison, should always be colder than the stars they orbit, that's just how physics works. But then there's KLT 9b, a planet that doesn't care about rules. This world defies logic, it's literally hotter than the star it circles. KLT 9b is a gas giant, superficially similar to Jupiter, but the resemblance ends there. It orbits its star so tightly, once every 1.5 Earth days, that it practically schemes the stellar surface. Its host star, KLT 9, is already a powerhouse, a blue-white giant far hotter and more massive than our Sun. Yet the planet's proximity means it gets bombarded with over 4,000 times the radiation Earth receives. The result? A planetary inferno with daytime temperatures soaring to 4,300 degrees Celsius, hotter than many small stars. That's right. A planet hotter than a star. At those temperatures, molecules can't survive. Not clouds, not water, not even hydrogen pairs. The heat rips them apart into individual atoms, turning the atmosphere into a swirling atomic soup, iron, titanium, hydrogen, all simmering in an endless furnace. But the chaos doesn't stop there. KLT 9b is evaporating. Its atmosphere is being stripped away by ultraviolet radiation, streaming into space like the tail of a comet. Astronomers estimate it's losing millions of tons of gas every second. Over time, it may completely disintegrate, boiled down to nothing. The planet is also tidally locked, meaning one side always faces the star while the other lives in perpetual night. But don't imagine cool darkness, the cold side still burns above 2,000 degrees, hot enough to melt metal. Even in shadow, it glows. The relentless radiation doesn't just scorch, it distorts. The planet's shape isn't a sphere but a stretched oval, gravity literally pulling it apart. It's an egg-shaped world, constantly twisted and strained, clinging desperately to coherence as it orbits near the Roche limit, the point where tidal forces could tear it to pieces. And to make it even stranger, KLT 9b orbits poles up, its orbit tilted nearly 90 degrees to the star's equator. Most planets circle along a flat plane, but this one plunges head-on across the star's poles, as if defying celestial etiquette. Scientists suspect a past gravitational encounter, maybe another planet kicked it off course, sent it spiraling into this death loop. However it happened, it's now locked in a dance of destruction, forever circling, forever burning. We can't see KLT 9b directly. Instead, astronomers detect it through transit photometry, watching how the star's light dims slightly as the planet crosses in front, and spectroscopy, which analyzes how the starlight filters through the planet's atmosphere. That's how we know what the planet is made of, or rather, what remains of it. The data reveals traces of vaporized iron, titanium, calcium, and sodium, even long hydrogen tails stretching into space. The atmosphere is so bloated from heat that it nearly brushes the star's surface. Everything about KLT-9b screams, impossible. It's too close, too hot, too tilted, and somehow still intact. It challenges our very definition of what a planet can be. We used to think gas giants only formed far from their stars, where temperatures were cool enough for gases to condense. For KLT-9b to exist, it must have migrated inward after forming, a cosmic daredevil drawn fatally close to its sun. It likely ricocheted through its system, brushing past other worlds before settling into its doomed orbit. Now it hangs there, defying survival itself, a world of atomic storms, metal vapor, and endless daylight. It's poetic in its own terrifying way. A planet too close to the flame, spinning through a storm so violent that even atoms can't hold together. In a universe that favors order, KLT-9b is a rebellion, too bright, too fast, too doomed, and utterly, undeniably real. The galaxy without dark matter. If there's one rule astronomers thought they could rely on, it's that every galaxy needs dark matter to stay together. That unseen, untouchable substance, invisible to light but heavy with gravity, is supposed to be the cosmic glue that holds galaxies in shape. Without it, stars would drift away, the spiral arms would unravel, and galaxies would simply fall apart. So when scientists stumbled upon a galaxy that appeared to have no dark matter at all, the entire field of astrophysics nearly short-circuited. It's called NGC 1052 DF2, or simply DF2 for short. At first glance, DF2 looks forgettable, a faint smudge of light, barely visible even through powerful telescopes. But appearances can lie. This ghostly patch of stars is one of the strangest discoveries in modern astronomy. DF2 floats about 65 million light-years away, roughly the same width as our Milky Way, but it contains only a tiny fraction of the stars. Think of a ghost version of our galaxy, same size, almost empty. A celestial balloon, inflated but hollow. When astronomers studied DF2's globular clusters, compact star groups orbiting within the galaxy, something didn't add up. The clusters were moving too slowly. In a normal galaxy, dark matter's extra gravity would pull them faster, keeping them tightly bound. But DF2's clusters drifted lazily, as if there were no hidden mass to tug them inward. It was the cosmic equivalent of realizing your house has no foundation and yet somehow hasn't collapsed. That discovery changed everything. If DF2 truly lacked dark matter, it shouldn't even exist, not by any model we have. Every galaxy we've ever studied needs a dark matter halo to stabilize it. Without one, stars should scatter into the void. But DF2 just sits there. Quiet, fragile, faint, and entirely wrong. At first, many doubted it. Maybe the measurements were off. Maybe the galaxy was closer than assumed, which would skew the math. Maybe the instruments were reading something strange in the background light. But in 2019, a second galaxy appeared, NGC 1052 DF4, a near twin, equally wispy and equally devoid of dark matter. That sealed it. This wasn't a glitch. There really are galaxies without dark matter. Which means two things: either our understanding of how galaxies form is incomplete, or the laws of gravity themselves need rethinking. Neither is a comforting option. So how could a galaxy lose its invisible scaffolding? One idea suggests DF2 was once part of a larger system that stripped away its dark matter during a violent collision, leaving behind only the luminous bits. Another theory argues that DF2 might have formed in a region of the universe where dark matter simply wasn't dense enough to accumulate, a kind of gravitational backwater. And then there's the wild possibility, whispered more than shouted, that maybe dark matter isn't universal at all. Maybe gravity behaves differently in certain environments, as some physicists propose in models like MOND, modified Newtonian dynamics, which tweaks the laws of gravity to account for strange galactic motion. It sounds fringe, but DF2 gives that idea a little more room to breathe. Before we rewrite physics textbooks, though, it's worth remembering that DF2 isn't alone in being weird. Other galaxies swing the opposite way, packed so tightly with dark matter that their stars whirl at impossible speeds. It's as if the universe can't decide how much invisible mass to use when assembling galaxies. Some hoard it like dragons, others go without entirely. DF2 itself is faint but visible. You can actually photograph it with the right equipment. Its ghostly structure barely glows, and its star clusters, the same ones that revealed its secret, shine unusually bright. They're like cosmic lanterns orbiting an almost hollow shell. After countless checks, the conclusion still stands: this galaxy has almost no dark matter. It doesn't mean dark matter doesn't exist, the weight of evidence across the cosmos still says it does, but galaxies like DF2 remind us that the universe is never one size fits all. Exceptions are where the real progress happens. They force us to rethink, to remeasure, to question the things we thought were constants. DF2, the ghost galaxy, shouldn't exist. And yet it drifts on, fragile and serene, a whisper of stars shining against the dark, a quiet rebellion against the invisible forces that bind everything else. A moon with an atmosphere, when its planet has none. If you were designing a solar system from scratch, you'd probably assume that the big worlds get the atmospheres. Planets should be the powerhouses, massive enough to trap gases and generate weather, while their moons remain cold, bare, and airless. That's how it works around Earth, Mars, and Jupiter. But space loves irony. Because orbiting Saturn is a moon that turns that logic upside down, a small, frozen world with a thick, hazy atmosphere, while the planets and moons around it sit naked and exposed. That moon is Titan. Titan isn't just any moon. It's the second largest in the solar system, only slightly smaller than Jupiter's Ganymede, and even bigger than Mercury. But its size isn't what makes it special. Titan has something no other moon has, a dense, layered atmosphere thicker than Earth's. From orbit, Titan looks like a blurry orange marble. Sunlight can't penetrate the haze, a golden smog that completely hides the surface. Beneath that haze lies a landscape both alien and familiar, rivers, lakes, and seas, not of water, but of liquid methane and ethane. It rains there, too. Clouds gather, storms form, and methane showers fall onto icy ground. The liquid collects into lakes, evaporates, and cycles back into clouds, a complete weather system, eerily mirroring Earth's hydrological cycle, only rewritten in hydrocarbons. Meanwhile, other moons, even ones larger than Titan, have none of this. They're frozen, cratered, and still. So how did Titan end up so alive? First, distance and cold. Titan orbits over 1 billion kilometers from the Sun, where the average surface temperature is a bone-cracking -179 degrees Celsius. At that temperature, water is hard as granite, and methane acts like water does on Earth, forming clouds, rivers, and rain. The cold also helps Titan hold on to its atmosphere. Its gravity is modest, only about 1/7 of Earth's, but the extreme chill slows gas molecules down, keeping them from escaping into space. Over time, this has allowed Titan to keep a thick atmosphere while larger but warmer worlds like Mars or Mercury lost theirs. Second, chemistry. Titan's air is about 95% nitrogen, like ours, but with a small dose of methane that makes all the difference. Sunlight breaks that methane apart, creating complex organic molecules, hydrocarbons that clump together into a haze. That haze scatters light and gives Titan its signature orange glow. It's like smog on a planetary scale, permanent and planet-wide. It's almost unfair how Earth-like Titan feels in the most alien way possible. There are dunes carved by wind, valleys etched by rainfall, and polar seas the size of the Great Lakes. The Cassini spacecraft, which orbited Saturn for over a decade, mapped them in detail using radar. When the Huygens probe parachuted to Titan's surface in 2005, it landed among frozen pebbles and methane mud, a snapshot of an active, living landscape. Here's the twist: Titan's parent planet, Saturn, doesn't even have a solid surface. It's a swirling globe of hydrogen and helium, with no clear boundary between gas and core. So in a way, Titan possesses something Saturn doesn't, a ground you could stand on, and an atmosphere thick enough to support flight. In fact, flight there would be easy. Titan's air is dense, and its gravity is weak, perfect conditions for flying. With wings strapped on, a human could theoretically lift off with a strong flap or two. That's why NASA's upcoming Dragonfly mission, launching in the late 2020s, is sending a drone there. It will soar across Titan's surface, sampling organics, sniffing the air, and searching for the chemistry of life. Yes, life. Because Titan isn't just a curiosity, it's a potential cradle for something extraordinary. Beneath its icy crust, scientists believe there's a liquid ocean, a mixture of water and ammonia warmed by tidal forces from Saturn's gravity. That means Titan might host two oceans, one of methane on the surface, and one of water deep below. Both could provide the right conditions for chemistry to begin, maybe even for life to exist. That's what makes Titan so mesmerizing. It's both alien and familiar, a moon with rain and rivers, clouds and seasons, and maybe the ingredients for life, orbiting a planet made of gas. And there's one last mystery: Titan has no magnetic field, yet somehow its atmosphere has survived for billions of years. Solar wind should have stripped it away long ago. Some scientists think the haze protects it, others believe Saturn's magnetic bubble shields it just enough. It might even be replenished constantly from Titan's interior, methane leaking upward like breath. Whatever the reason, it stands as one of the solar system's strangest contradictions, a small, frozen moon with more atmospheric depth than worlds 10 times its size. Titan should not have an atmosphere. It should not have rain, dunes, or lakes. And yet it does, quietly rewriting the rules of what a moon can be. If there's life beyond Earth, Titan might be the first place we find it, not swimming in water, but drifting in methane clouds beneath an orange sky. The star that survived a supernova. There are few events in the cosmos more violent than a supernova. It's the grand finale of a star's life, a flash of energy so immense that, for a moment, it can outshine an entire galaxy. When a supernova erupts, everything near it should be erased. But one star broke that rule. It was blasted by a supernova and lived. Not metaphorically. Literally. A nearby star endured the detonation of its companion, a thermonuclear blast releasing the energy of several octillion nuclear bombs, and somehow walked away. Astronomers call it LP 40-365. It's about 2,000 light-years from Earth, and at first glance it looks ordinary, a faint white dwarf glowing softly against the dark. But the closer scientists looked, the stranger it became. First clue, its speed. LP 40-365 is sprinting through space at over 850 kilometers per second, nearly 2 million miles an hour. That's fast enough to escape the Milky Way completely. Stars simply don't move that fast unless something catastrophic kicked them. Then came clue number 2, its composition. Typical white dwarfs are built from carbon and oxygen, the ashes of a dead sun. But LP 40-365's surface is rich in heavier elements, iron, manganese, nickel, the kind forged in supernova explosions. Its skin is literally burned with the chemical fingerprints of nuclear fire. Put the pieces together and the story becomes clear. Once upon a time, LP 40-365 orbited another star in a tight binary pair. Its partner grew unstable and exploded in a Type Ia supernova, the kind used as cosmic mile markers because they always detonate with similar brightness. That blast should have vaporized everything nearby, including LP 40-365. But instead of dying, it was flung outward, scorched but intact. Imagine standing beside a volcano when the mountain itself erupts, and somehow you're not destroyed, just hurled into the sky, burned and stripped, but alive. That's what this little white dwarf did. Its outer layers are gone. Its hydrogen and helium burned off in the blast. What remains is a core of dense metal and radioactive scars, a half-star, half-corpse still glowing with leftover heat. Scientists sometimes call it a zombie star, something that died but didn't stay dead. Even stranger, LP 40-365 is less massive and more bloated than typical white dwarfs. It shouldn't hold together, and yet it does. Some researchers think it wasn't merely a survivor of the explosion, it may have been part of the explosion itself. In one possible scenario, two white dwarfs spiraled together, feeding off each other until one detonated. The blast tore them apart, burning one completely and half-igniting the other. The surviving fragment, our LP 40-365, was flung into the void, still carrying the nuclear shrapnel of its partner. This, partially burned runaway, theory has gained traction because astronomers have since found others like it, small, fast-moving white dwarfs scarred with heavy elements. LP 40-365 may be just the first of a hidden population, the supernova veterans of the Milky Way. Today, LP 40-365 races through space alone, exiled from the galaxy that birthed it. In a few 100 million years, it will drift beyond the Milky Way's edge into intergalactic night, a wandering ember carrying the memory of a stellar apocalypse. The rules said no star could survive a supernova. LP 40-365 didn't care. A planet that rains glass sideways. Now, let's visit a world so extreme it feels like punishment just to describe it. A place where the sky glows blue, the wind screams faster than bullets, and molten glass falls as rain, not down, but sideways. Welcome to HD 189733b, one of the most hellish exoplanets ever found. It's a hot Jupiter, a gas giant roughly the size of Jupiter but orbiting its star 30 times closer than Earth orbits the Sun. It completes a full year in just over 2 days. That proximity cooks the planet to over 1000 degrees Celsius, hot enough to melt rock and vaporize clouds. HD 189733b is also tidally locked, which means one hemisphere always faces its star in endless daylight while the other remains in perpetual night. The heat difference between those sides drives winds that tear around the planet at more than 2 kilometers per second, that's 7 times the speed of sound. Imagine hurricanes so powerful they wrap completely around the globe, dragging the atmosphere sideways in a permanent cyclone. Now add glass. The planet's atmosphere contains silicate particles, tiny grains similar to sand and quartz. Under such blistering temperatures, those particles melt into droplets of glass. Then, as the wind races from the day side to the night side, those droplets get blown horizontally at supersonic speeds. If you could stand there, which you absolutely could not, the air would slice you to pieces. It's not rain as we know it. It's a storm of liquid blades, hissing sideways across a burning sky. Despite the violence, from far away this world looks almost serene. The Hubble Space Telescope captured its hue in visible light, a brilliant, oceanic blue. But that color isn't from water. It's caused by the way the silicate particles scatter blue wavelengths, the same physics that makes Earth's sky blue, just magnified and deadly. So when you see HD 189733b rendered as a calm azure globe, remember, that beauty hides chaos. It's a planet being shredded by its own weather. The more scientists study it, the stranger it gets. Its atmosphere doesn't just move fast, it expands. The upper layers are so heated that they puff outward until they nearly graze the star's surface. Streams of gas escape into space, turning the planet into a slow-motion comet. And it's not alone. Astronomers suspect there are many worlds like this, hot Jupiters, whose skies rain molten minerals, corundum, iron, even rubies or sapphires, depending on chemistry. In exoplanet weather forecasts, stone and metal showers are just another day. HD 189733b remains the archetype, the poster child of atmospheric insanity. No ground. No calm. Just blue light, screaming winds, and storms of glass sharp enough to carve mountains, if there were any mountains left to carve. From a distance, it glimmers like paradise. Up close, it's a nightmare painted in sapphire. Dark energy, the force that pushes the universe apart. Of all the mysteries hanging over modern physics, none is bigger, or quieter, than the one literally stretching the universe beneath our feet. Something unseen is pushing galaxies away from each other, not gently, not gradually, but faster and faster. It's as if space itself is under tension, expanding like a balloon that refuses to stop. Astronomers call that something dark energy. We don't know what it is. We only know it exists. And that it makes up almost 70% of everything. For most of human history, the cosmos seemed stable. Gravity was the rulemaker, matter pulls matter, galaxies should slow down over time. After the Big Bang flung everything outward, surely gravity's tug would begin to rein it all in. But in the 1990s, two independent teams studying distant supernovae discovered the unthinkable. Those ancient explosions were dimmer than expected. Dimmer meant farther. Farther meant the universe hadn't been decelerating, it had been accelerating. Something stronger than gravity was at work, spreading the galaxies apart. That revelation rewrote cosmology overnight. The universe wasn't coasting, it was speeding up. To explain it, scientists resurrected a ghost from Einstein's equations, the cosmological constant. He'd invented it in 1917 to keep the universe static, then later called it his greatest mistake. But maybe it wasn't a mistake at all. Maybe space has its own built-in energy, a pressure that doesn't fade as space expands, but instead creates more of itself the more room there is. Think of dark energy as the opposite of gravity. Where gravity pulls, dark energy pushes. And the bigger the universe gets, the more push there is to go around. It doesn't clump like matter. It doesn't shine or scatter light. It seems perfectly uniform, filling every corner of space with an invisible pressure that never weakens. Imagine an ocean that rises as it flows outward, the farther it stretches, the deeper it gets. Because of that runaway pressure, galaxies are being carried away faster than light, not through space, but with it, as the fabric of the universe itself expands. If dark energy keeps winning this cosmic tug-of-war, distant galaxies will drift beyond visibility. Billions of years from now, their light will never reach us again. Future astronomers, if anyone's left, will look at the night sky and see nothing beyond their own galaxy, unaware that the universe was once filled with billions more. That's not poetic exaggeration. It's the mathematical consequence of acceleration. So what could dark energy be? Physicists have a few guesses, each stranger than the last. 1. Vacuum energy. Quantum theory predicts that even empty space isn't truly empty, it seethes with virtual particles blinking in and out of existence. Maybe those fluctuations add up to a small but constant pressure. The problem? Our calculations overshoot reality by about 120 orders of magnitude, the worst prediction in the history of science. 2. Quintessence. Perhaps dark energy isn't constant at all but a dynamic field that evolves over time, a kind of cosmic weather pattern that waxes and wanes. It could decay, strengthen, or even reverse. If it grows stronger, it might one day rip everything apart. 3. Modified gravity. Maybe gravity itself changes on immense scales. Einstein's equations have never failed in our solar system, but perhaps across billions of light-years, the geometry bends differently. Some models add a repulsive twist to gravity at large distances. 4. The Big Rip. The nightmare scenario. If dark energy keeps intensifying, its expansion could eventually overwhelm every binding force in existence, tearing galaxies, stars, planets, even atoms into dust until spacetime itself unravels. Right now, we simply don't know which, if any, is true. What we do know is that dark energy exists, because everything else we can measure says it must. It's humbling to realize that 95% of the cosmos, dark energy plus dark matter, is invisible, intangible, and unexplained. The luminous world we see, the stars and nebulae and you and me, make up only the leftover 5%. We live inside a universe whose driving force we can't see, whose purpose we can't guess, whose power silently outpaces everything we know. Dark energy doesn't shine, but it decides how the story ends. And the ending, as far as we can tell, is still accelerating. A neutron star that spins 700 times per second. Now swing from the largest scale imaginable to one of the smallest, and fastest. Picture a sphere the size of a city, barely 20 kilometers wide, yet heavier than the sun. Now spin that object 700 times every second. That's not science fiction. That's PSRJ 1748-2446 AD, the fastest spinning neutron star ever found. It whirls at 43,000 revolutions per minute, faster than any engine, any drill, any machine humanity could build. Its equator moves at roughly a quarter of the speed of light. Neutron stars are what remain when massive suns die but stop short of becoming black holes. In a supernova's aftermath, gravity squeezes the star's core so violently that protons and electrons merge into neutrons, leaving behind a sphere of nuclear matter, a single atomic nucleus the size of Manhattan. A teaspoon of that material would weigh 1 billion tons. Many neutron stars rotate rapidly right from birth, conserving angular momentum as they collapse, like an ice skater pulling in her arms. But the fastest ones, called millisecond pulsars, didn't start that way. They were spun up over millions of years by stealing energy from a companion star. As gas spirals from the companion, it forms a glowing accretion disk that drizzles matter onto the neutron star's surface. Each drop adds angular momentum, turning the star faster and faster until it becomes a blur. PSRJ 1748-2446 AD has reached that razor's edge. If it spun just a heartbeat faster, centrifugal force might tear it apart. It's balanced perfectly between gravity and momentum, a cosmic gyroscope defying disintegration. And it's not just spinning, it's pulsing. A neutron star's magnetic poles shoot out beams of radiation, and as it turns, those beams sweep across space like lighthouse beams. To an observer on Earth, each rotation produces a pulse of radio waves, hundreds every second. The timing is so precise that astronomers use these pulses as galactic clocks. Their regularity rivals the stability of atomic clocks on Earth. A network of millisecond pulsars could one day serve as a deep space GPS, mapping the galaxy through dead stars' heartbeats. PSRJ 1748-2446 AD lives in Terzan 5, a dense globular cluster packed with ancient stars 18,000 light-years away in Sagittarius. Such crowded neighborhoods are ideal for creating exotic systems, collisions, captures, gravitational slingshots, so it's no surprise a record-breaker lives there. What is surprising is how calm it seems. Despite spinning faster than any known object, it holds together silently. Its surface tension, powered by nuclear forces, is so strong that mountains on it can rise only millimeters high. Anything larger would collapse instantly under gravity's pull. If you could stand near its equator, ignoring the impossible radiation, you'd be moving at 70,000 kilometers per second. A single second for you would tick differently from a second on Earth. Time itself bends around such density. We can't see it with our eyes, but its rhythm hums through radio telescopes, tick tick tick, 700 times each second, the sound of a star that refuses to slow down. And here's the haunting thought, we might not yet have found the fastest one. Somewhere out there could spin a neutron star turning even quicker, its beam never quite aimed our way. The galaxy could be full of these invisible engines, each a relic of stellar death still whirling with unstoppable momentum. When you think of speed, jets, bullets, comets, remember this. A dead star 18,000 light-years away is outspinning them all, every fraction of a second, its rhythm older than civilization and faster than thought. The universe, it turns out, keeps its own tempo, and it's measured in hundreds of beats per second. The coldest place in the universe, colder than space itself. Space is cold. Colder than anything we can imagine on Earth. Between galaxies, the temperature of the cosmic background, the faint radiation left over from the Big Bang, hovers just above absolute zero, at 2.7 Kelvin. That's minus 270 degrees Celsius, only a few degrees above the lowest possible temperature in nature. But there's one place in the known universe that's even colder than that. Colder than the void. Colder than the empty dark between galaxies. It's called the Boomerang Nebula, and it's the coldest natural object ever found. This fragile, ghostly cloud lies about 5,000 light-years away in the constellation Centaurus. At its heart is a dying star, a red giant nearing the end of its life. As it sheds its outer layers, the gas expands rapidly into space, forming a delicate hourglass shape that stretches across a full light-year. That expansion is the secret to its unimaginable cold. Just like air cools when it expands, the same principle that makes a refrigerator work, the Boomerang Nebula's gas has spread outward so fast that it's cooled to a record-breaking 1 Kelvin, or minus 272 degrees Celsius. That's colder than the background radiation of the universe itself. It's so frigid that if you could somehow touch it, heat would rush out of your hand into the nebula. Space itself would feel warm by comparison. From telescopes, it appears as a faint, blue-tinted ghost, twin lobes of mist radiating from a bright central star. Early observations with the Atacama Large Millimeter Array revealed how the gas moves, expanding outward at nearly 600,000 kilometers per hour, faster than any ordinary stellar wind. That velocity explains the temperature drop. The faster it expands, the more it chills. The result is like a cosmic freezer, a temporary, delicate balance of motion and cold that will vanish once the expansion slows. Over time, ultraviolet light from the central star will heat the gas again, transforming the Boomerang Nebula into a more typical planetary nebula glowing with color and warmth. But right now, in this sliver of cosmic time, it's a bubble of extreme stillness in an otherwise burning universe. The irony is almost poetic. Stars spend their lives as furnaces, forges of fire and fusion, only to end their days wrapped in the coldest cloak imaginable. The Boomerang Nebula isn't just a monument to temperature, it's a portrait of death slowing down. Its name, Boomerang, comes from the shape astronomers once thought they saw, a curved structure flaring from a bright center. Later, higher-resolution images revealed a more symmetrical hourglass. But the name stuck, fittingly whimsical for something so otherworldly. Scientists believe the nebula's star might actually be a binary system, and that gravitational interactions between the two stars are what caused the gas to shoot out so fast. Like a balloon squeezed at the center, it forms twin outflows of material rushing away in opposite directions, the shape of breath exhaled into the void. The Boomerang Nebula reminds us that empty space is never quite what it seems. Even the vacuum between stars glows faintly with heat. Yet here is a pocket of reality that has somehow dipped below that cosmic minimum, an island of silence colder than the rest of existence. It's a glimpse into the edge of thermodynamics, a brief moment where the universe has accidentally outcooled itself. And as strange as it sounds, it won't last. In a few thousand years, an eye blink on astronomical scales, that chill will fade, replaced by the warmer glow of stellar remnants. Until then, the Boomerang Nebula remains the coldest place known, a breath frozen in the dark, whispering slower than time itself. A black hole that sings in sound waves. When we think of black holes, we think of silence, places where light dies, where nothing escapes, where even sound itself should have no meaning. But the universe, it turns out, can make even black holes sing. In 2003, astronomers using NASA's Chandra X-ray Observatory detected something haunting in the heart of the Perseus galaxy cluster, 250 million light-years away, a sound wave, rippling through intergalactic gas. Not metaphorically. A literal sound wave, a deep, slow vibration resonating from a supermassive black hole. The wave's frequency is 57 octaves below middle C, a B-flat so low it's physically impossible for the human ear to hear. The wavelength of this cosmic note spans 30,000 light-years. To give you an idea, if you could somehow amplify it into the audible range, it would be like a single, endless hum, one cycle every 10 million years. It is, technically, the deepest note in the universe. So what's making it? At the center of the Perseus cluster lies a monster black hole, billions of times the mass of the Sun. As matter falls toward it, the black hole occasionally burps, not with light, but with jets of energy shooting out at near light speed. These jets push against the hot gas that fills the cluster, carving vast cavities in the plasma and sending pressure waves rippling outward. Those waves travel like sound through air, just slower, through much thinner material. Over millions of years, they propagate across hundreds of thousands of light-years, shaping the gas in rhythmic patterns like ripples on a pond. If you could somehow hear it, it wouldn't be a melody or a roar. It would be an eternal drone, a subsonic heartbeat humming through the dark. And this black hole doesn't just sing once. It's been vibrating its environment for over 2 billion years, feeding and pulsing in cycles that sculpt the entire cluster around it. The energy released in one of these outbursts is equivalent to trillions of supernovae. To visualize it, imagine a single pebble thrown into a cosmic ocean, and the ripples it creates are the size of galaxies. Black holes are often described as destroyers, but in reality, they can be creators, too. The pressure waves from these outbursts help regulate star formation, preventing the surrounding gas from cooling too quickly. Without that feedback, entire galaxies would grow uncontrollably dense. In a strange way, the black hole's song is also a form of balance, a cosmic metronome keeping its galaxy cluster in rhythm. Astronomers later converted the data into audible sound by scaling the frequency up trillions of times. The result is eerie, a droning hum that rises and falls like breath, like the universe exhaling through an unseen throat. It's one of the few times we've literally heard a black hole. And yet, it's not the only one. Other clusters show similar ripples, echoes of activity in their central black holes. Space, for all its emptiness, carries memory. These waves travel for millions of light-years, etching the rhythm of creation and destruction into the fabric of gas and dust. The idea that something which swallows light can also produce sound seems paradoxical. But that's the beauty of it. What we call sound is just vibration, and vibration doesn't need air, only matter to move through. In the vast atmospheres of galaxy clusters, even silence has a frequency. So somewhere, across 250 million light-years, a black hole is humming a single, endless note. Not of doom, but of structure. Not chaos, but balance. A sound so low and so slow that it will keep playing long after our sun has turned to dust. The deepest sound in the universe isn't heard. It's felt. A planet with 3 suns. Every child who's seen Star Wars remembers that iconic shot, Luke Skywalker standing on a desert plain, staring out at 2 suns setting side by side. For decades, that image felt like fantasy. But then science caught up, and reality, as always, went further. Astronomers discovered a world that doesn't orbit 1 sun, or even 2. It orbits 3. A planet with 3 suns blazing across its sky. It's called HD 131399 UP, and it lies about 340 light-years away, in the constellation Centaurus, the same cosmic neighborhood as the diamond star Lucy. When it was first found in 2016, it instantly became one of the strangest exoplanets ever observed. Imagine standing on its surface, if you somehow could. The sky would never fully darken. Depending on where you stood in its orbit, you might see all 3 suns at once, casting triple shadows across the ground. Sometimes 2 would set together, leaving one to hang like a ghostly lantern, keeping the world in an eternal twilight glow. It's the kind of light show that no artist could fully capture. HD 131399 UP is a gas giant, about 4 times the mass of Jupiter, orbiting within a triple star system. Here's how it works. One bright star, called HD 131399A, dominates the system. Farther out, at about 300 astronomical units away, that's 10 times Pluto's distance from the Sun, 2 smaller stars, HD 131399b and HD 131399c, orbit each other as a binary pair. The planet moves around the main star, but the entire trio of suns remains gravitationally linked, a delicate, gravitational dance. The strange part? HD 131399Ab's orbit is precariously wide. It swings so far from its main star that it comes dangerously close to the gravitational pull of the other two. By most models, it shouldn't even be stable. It's living on the edge of chaos. In simulations, even a small shift could fling it into space or tear it free to orbit the binary pair instead. Some astronomers think it might not last more than a few million years before being ejected entirely, a cosmic orphan. But for now, it remains, circling amid the light of three suns. If you stood there during what passes for daytime, you'd see all three stars blazing together. When night fell, if it ever truly did, the combined glow would still be hundreds of times brighter than our full moon. Shadows would overlap and blur, color and direction would lose meaning. It's not the only triple-star planet either. Others have been found since, some stable, some chaotic, all extraordinary. These systems force astrophysicists to rethink how planets form. For a world to take shape in the gravitational tug-of-war of three suns is like trying to build a sandcastle between colliding tides. And yet somehow, nature managed it. HD 131399 AB's temperature and composition mark it as a young planet, only about 16 million years old. Its atmosphere glows faintly from the leftover heat of formation, shining bright enough for astronomers to image it directly using the European Southern Observatory's Very Large Telescope in Chile. That's how we know it's real, not an indirect shadow or a wobble, but an actual dot of light, a planet photographed under alien suns. 3 stars, 1 world, endless motion. It's humbling to realize that our solar system, with its single, stable sun, might actually be unusual. The majority of stars in the galaxy exist in binary or multiple systems. Double and triple suns may be the cosmic norm, not the exception. In that sense, HD 131399 AB isn't the outlier, we are. So when you look up and see one sun setting, remember, somewhere, another sky holds 3, rising, burning, and setting in harmony. A world of perpetual dawns and dusks, bathed in golden light that never quite fades. A place where night is just a rumor. The loneliest galaxy in the universe. Some galaxies live in crowds, great cosmic cities bound by gravity, clustered in superclusters stretching for hundreds of millions of light-years. And then there are the wanderers. The ones drifting far beyond their peers, surrounded by nothing but black. Meet MNG 0046, sometimes called the loneliest galaxy in the universe. It floats in a void so vast that no other galaxies lie within hundreds of millions of light-years. Imagine standing on a world inside it, looking up into a night sky nearly empty of other galaxies, only a few faint smudges where billions of stars used to be visible. In human terms, this is cosmic solitude. The universe isn't evenly packed. It's built like foam, clusters and filaments of galaxies forming the walls, while vast voids make up the gaps in between. These voids can be 100 to 500 million light-years wide, empty bubbles in the cosmic web. MNG 0046 sits right in the center of one of these voids, an island of light adrift in darkness. We don't know exactly how it got there. Maybe it formed where it stands, a lonely spark born in a region that never filled with matter. Or perhaps it was thrown out, gravitationally ejected from a galaxy cluster after a collision, doomed to drift forever. Whatever the reason, it now lives without neighbors. Galaxies rely on interaction to evolve. Collisions trigger starbursts, tidal forces stir up gas, mergers feed black holes. But MNG 0046 has none of that. It hasn't collided, hasn't merged, hasn't been disturbed in billions of years. Its stars simply age and fade in perfect silence. That silence, though, makes it scientifically precious. Because it's isolated, astronomers can study it as a kind of control sample, a galaxy unshaped by external forces. Its structure shows what a galaxy might look like if left alone since birth. Surprisingly, it's still beautiful. Spiral arms, blue clusters, and faint dust lanes ripple through it, proof that even in isolation, creation continues. Inside its disk, gas still collapses into stars. It may be lonely, but it's not dead. Telescopes can spot MNG0046 because even the loneliest light travels eventually. When we see it as it was hundreds of millions of years ago, a single galaxy burning quietly in a sea of nothing. There's something profoundly human in that image. A luminous being adrift in endless dark, still shining simply because it can. In a universe where gravity builds connections, where galaxies form entangled webs, this one stands apart, a reminder that even isolation can create beauty. Its existence also tells us something about cosmic architecture. The universe, on the grandest scale, is not uniform. For every crowded cluster bursting with activity, there are empty voids almost completely barren. Galaxies like MNG0046 mark the edges of those hollows, boundary lights flickering between presence and absence. If you could somehow travel there, cross billions of kilometers of emptiness and arrive in its orbit, you would see a sky unlike anything imaginable. Fewer stars. Fewer galaxies. A darkness so total it would feel physical, pressing in from all sides. And yet, at its heart, MNG0046 would still spin serenely, its spiral arms glowing faintly blue, its stars orbiting in peace. No collisions. No interruptions. Just a galaxy aging in silence. It's a paradox, the loneliest place in the cosmos, and perhaps one of the most stable. Because while the clustered galaxies tear each other apart through gravitational chaos, the loner survives, untouched, unchanged, and utterly alone. The rogue planet drifting in darkness. Not every planet has a home. Some worlds are born into chaos, thrown from their birth systems, left to wander through the endless dark between stars. They have no sunrise, no orbit, no warmth, only the faint memory of the star that once held them close. These are the rogue planets, the cosmic orphans. Astronomers believe there could be billions of them drifting through our galaxy, maybe even more than the number of stars themselves. Invisible, silent, and cold, they travel endlessly through space, bound to nothing but gravity's faint whisper. The first such world ever directly detected is called Kepler 2149-0403, about 100 light-years away. When it was discovered, scientists weren't sure what they were looking at, a failed star or a planet gone astray. But its size, temperature, and spectral fingerprint all pointed to one conclusion: it was a free-floating planet roughly the mass of Jupiter, roaming through interstellar space without a sun. Imagine standing on such a world. Above you, no dawn would ever come. The sky would be black forever, littered with frozen stars. The only light might come from the planet's own faint heat, a dim infrared glow bleeding from its core. If it once had moons, they'd circle like ghosts, illuminated only by starlight from galaxies unimaginably far away. How do planets like this come to be? Some are born free, forming directly from collapsing gas clouds like stars do, but too small to ignite fusion. Others are exiles, flung away by gravitational violence, kicked from their systems after close encounters with bigger planets or passing stars. Early in a solar system's life, chaos reigns. Orbits cross, collisions happen, giants migrate inward and outward. In that celestial shuffle, smaller worlds can get catapulted into deep space. One moment they orbit in sunlight, the next, they're gone, cast out forever. It sounds tragic, but it's also strangely poetic. Because even in the darkness, these planets still exist. Some may carry thick atmospheres that trap residual heat, keeping subsurface oceans from freezing solid. Others might have internal radioactive decay or tidal flexing that keeps their cores warm. In theory, a rogue planet could still harbor life, hidden beneath an icy crust, thriving in eternal night. NASA scientists once imagined a world like this, Steppenwolf, they called it, a rogue Earth, wandering through interstellar space. If such a planet had a thick enough hydrogen atmosphere, it might preserve heat and pressure enough to maintain liquid water under the ice. Entire ecosystems could exist, never seeing the light of any sun. Some rogue planets travel alone, but others might drift in pairs or clusters, the shattered remnants of a broken solar system. A few might even wander close enough to other stars to steal a brief warmth before moving on again. We've never visited one. We've never seen one up close. But we've found their faint signatures through the way they microlens, bending background starlight as they pass in front. That gravitational distortion is how we know they're out there, floating invisibly between the constellations. In the Milky Way alone, there could be trillions. An invisible population of worlds unlit, unanchored, unseen, each one a dark story of loss and survival. If you could drift alongside one, you'd see nothing ahead but black, nothing behind but black, and perhaps, once in a million years, the brief glow of a distant star fading like a memory. They are the wanderers of the galaxy. Planets without orbits. Homes without suns. Worlds that remind us that even in the vast, cold dark, existence goes on, quietly, stubbornly, endlessly. A star that eats its planet. Now imagine the opposite. Instead of a planet cast away by its star, picture a star that devours its planet whole. This isn't poetic symbolism. It's cosmic cannibalism, and it happens more often than you'd think. For years, astronomers suspected that as stars age and expand, they might swallow any nearby worlds. But in 2023, for the first time in history, scientists actually caught one in the act. The event occurred about 12,000 light-years away, in the constellation Aquila. There, a sun-like star was observed suddenly brightening, not explosively like a supernova, but in a slow, smooth flare that lasted about 10 days. At first, researchers thought it might be a binary outburst, two stars colliding. But when they analyzed the light, they realized it wasn't big enough for that. The object being devoured was far too small. It wasn't another star. It was a planet, roughly the size of Jupiter. What they had witnessed was a world being engulfed by its own sun, a process known as stellar engulfment. Here's how it works. As stars like ours run out of hydrogen, they expand into red giants. Their outer layers balloon outward, swallowing nearby planets like a tide rolling over islands. For Earth, that fate lies about 5 billion years in the future, when our sun will swell large enough to consume Mercury, Venus, and probably us. When that happens, the engulfed planet spirals inward through the star's atmosphere, creating shock waves and heating the gas. The star brightens, the atmosphere swells, and material flares outward in a glowing halo. The whole event may last only a few days, but its signature is unmistakable, a sudden, brief gleam of light in the infrared spectrum. That's what astronomers saw in Aquila. For the first time ever, they caught a planet in its final, fiery descent, disappearing into the star that gave it life. Afterward, the star dimmed again, but traces of the event lingered, gas and dust expelled outward, the ashes of a destroyed world. It's sobering to realize that this is our future. Someday, Earth too will face that same fate, a slow, graceful death inside an expanding sun. Oceans will boil, rocks will melt, and our planet will spiral inward until it dissolves into plasma. For a few brief days, our sun will flare with that same eerie brilliance, one last light before it settles into a white dwarf. But there's beauty in that violence. Because in swallowing its planets, a star also enriches itself. The heavy elements from the planet, iron, silicon, carbon, mix into the star's outer layers, altering its spectrum. In that sense, the world doesn't vanish completely, it becomes part of the star's chemistry, its legacy imprinted in light. Astronomers now hunt for these spectral fingerprints, the signs of stars that have eaten their own worlds. Some are surprisingly common. In fact, estimates suggest that up to 1 in 4 sun-like stars may have consumed at least one planet during their lifetime. It's the ultimate circle of cosmic life. Stars give birth to planets, planets orbit them for billions of years, and eventually, the cycle reverses, the Creator reclaims its creation. The story of a planet's end isn't just tragedy, it's transformation. The world that once basked in light becomes part of that light. A planet becomes starlight once more. The immortal storm on Jupiter. There's a storm on Jupiter that has been raging for at least 400 years, maybe even longer. It's larger than the entire planet Earth, spins faster than a hurricane, and glows crimson in the pale light of the outer solar system. We call it the Great Red Spot, but that name hardly captures its scale. This is not a storm like any we know. It's a monstrous anticyclone, a whirlpool of ammonia clouds and hydrogen gas big enough to swallow 3 Earths whole. It rotates counterclockwise at over 430 km per hour, forming an immense oval that has remained in Jupiter's atmosphere since at least the 1600s, when early astronomers like Giovanni Cassini first glimpsed it through primitive telescopes. Think about that. When Cassini looked up and sketched that swirling mark, empires still ruled continents, telescopes were new, and the concept of planetary weather didn't even exist. And yet, that same storm is still alive today. So why hasn't it died? On Earth, hurricanes eventually lose energy when they drift over land or colder water. But Jupiter has no land, no oceans, just an endless sea of gas and heat. The Great Red Spot feeds on Jupiter's internal energy, the heat rising from the planet's core, and the fierce jet streams that encircle its atmosphere. The result is a storm that never runs out of fuel. The deeper mystery, though, is that it has been changing. Spacecraft like Voyager, Galileo, and Juno have shown that the Great Red Spot is shrinking. It used to stretch more than 40,000 kilometers across, wide enough to fit 4 Earths. Now it's closer to 16,000. It's also growing taller and redder. No one knows exactly why. Some scientists think smaller storms are merging into it, feeding its rotation but altering its structure. Others suspect that chemical reactions high in its clouds, triggered by sunlight, are deepening its color. The red of the Great Red Spot is actually deceptive. It's not a true pigment but a complex interplay of sunlight, sulfur, and organic molecules reacting with ammonia. Under different lighting, the storm can appear orange, brown, or even salmon pink. Beneath the swirling clouds, Jupiter's atmosphere plunges deep, thousands of kilometers of gas compressed under colossal pressure. The storm itself may extend hundreds of kilometers downward, possibly rooted in a layer where hydrogen becomes a metallic fluid. That means the Great Red Spot isn't just a surface storm, it's a column of rotating atmosphere that pierces deep into Jupiter's body. It's also hot. Infrared measurements show that the region above the storm is hundreds of degrees warmer than the surrounding air, likely because the fierce winds generate heat through friction. And it's loud. If sound could travel through Jupiter's dense clouds the way it does on Earth, the Great Red Spot would thunder with a constant, low roar, the voice of a storm that has never stopped. No human has ever seen the start of it, and none alive today will see its end. When it finally fades, it will mark the close of a chapter that began before modern science itself. In that sense, the Great Red Spot is more than just weather, it's history made of wind. A living relic of time, spinning endlessly under the pale light of a distant sun. The star that shouldn't exist. The laws of physics are supposed to be unbreakable. Yet the universe has a way of bending its own rules, especially when it comes to stars. Among the billions scattered across the Milky Way, one star stands out not because it's bright or beautiful, but because it shouldn't be here at all. Its name is SMSSJ 031300.36-6708339.3, mercifully shortened to SMSSJ 0313-6708, and it's among the oldest known stars in the universe. When astronomers studied its spectrum, the unique fingerprint of light emitted by its atoms, they discovered something baffling: it contains almost no iron at all. That might not sound dramatic, but it rewrites everything we thought we knew about star formation. You see, the first stars ever born, the so-called population 3 stars, were made entirely of hydrogen and helium, the only elements created in the Big Bang. They were enormous and short-lived, burning out after just a few million years and exploding as supernovae, seeding the cosmos with heavier elements like carbon, oxygen, and iron. Every generation of stars that followed formed from that enriched material. Our Sun, for example, carries traces of many earlier stars that died before it, cosmic recycling on a grand scale. But SMSS J0313-6708 breaks that lineage. It has almost no iron, less than 1/10,000,000th the amount found in the Sun. That means it must have formed from gas polluted by only a single, tiny supernova, or perhaps none at all. In other words, it's a living fossil from the dawn of time. Astronomers estimate it's over 13.6 billion years old, born when the universe itself was less than 200 million years old, just a few cosmic heartbeats after the Big Bang. It's faint, small, and ancient, a dim red star still quietly burning hydrogen after all these eons. Its simplicity makes it a window into an era we can't otherwise see. The mystery deepened when scientists realized it shouldn't exist. By all our models, the first stars were supposed to be massive, hundreds of times the Sun's mass, and to explode violently, leaving behind black holes, not survivors. Yet here is SMSS J0313-6708, small, steady, and old enough to have witnessed the birth of galaxies. How did it form? One idea is that a small pocket of gas, left untouched by the heavy elements of supernovae, cooled slowly and fragmented, forming this single, low-mass star that never burned fast enough to die. Another possibility is that the supernova that enriched its region was unusually weak, scattering only the lightest elements. Either way, SMSS J0313-6708 shouldn't have lasted this long, but it did. It burns so efficiently that it may outlive the universe as we know it. While massive stars die young, small red dwarfs like this one can survive trillions of years. Long after our Sun fades into a white dwarf, SMSS J0313-6708 will still be shining faintly, its light stretching into eternity. When we look at it, we're looking across nearly the entire history of time, back to a universe still glowing from creation, when galaxies were newborn and light had barely learned how to travel. This single, dim star carries the memory of the beginning itself. It's proof that survival sometimes means simplicity, that even in a universe of violence and fire, something small, quiet, and old can endure through every storm. The star that shouldn't exist became the one that never stopped burning. The galaxy made entirely of dark matter. Imagine a galaxy you can't see. Not because it's far away, but because it's made almost entirely of dark matter, that mysterious, invisible substance that outweighs all visible matter in the universe 5-1. Astronomers have long known dark matter is real, even though they've never seen it directly. Its gravity bends light, shapes galaxies, and holds the cosmic web together. But it's always been the unseen scaffolding, the invisible frame around the visible. Then came a discovery that turned that balance upside down, a galaxy with no stars. In 2018, scientists using the ALMA observatory in Chile found something extraordinary, a faint, misty object named Dragonfly 44, located about 330 million light-years away in the Coma cluster. At first, they thought it was a ghost galaxy, nearly empty of stars. But when they measured how its few remaining stars moved, the numbers didn't make sense. Those stars were orbiting far too fast. By all calculations, Dragonfly 44 should have flown apart long ago. The only explanation was that it contained a massive halo of invisible matter, roughly the same mass as the Milky Way, but with less than 1% of the stars. In other words, a galaxy built of dark matter itself. No one had ever seen anything like it. It glows faintly, a dim smear of starlight surrounded by an enormous gravitational presence we can't detect except through motion. Imagine a ghost the size of a galaxy, bending light around it, holding its structure together without ever shining. We're not entirely sure how such galaxies form. One theory suggests they began like normal galaxies but had their gas stripped away early, maybe by violent winds or collisions, halting star formation before it began. Others think they might be failed galaxies, places where dark matter collected but the conditions for light never followed. In Dragonfly 44's case, the evidence points to an extreme imbalance, 99.99% dark matter, 0.01% visible matter. The ratio is almost absurd, a structure made of pure gravity, with a sprinkle of stars marking where the edges are. Observations with newer instruments have since refined the data. Dragonfly 44 may have slightly less dark matter than first believed, but its significance remains the same. It's one of the darkest galaxies ever found. And it's not alone. Other galaxies with similar properties have appeared, dim and ghost-like, scattered across the universe like hidden bones beneath the cosmic flesh. Each one whispers the same truth: most of the universe isn't what we see. Dark matter doesn't glow, doesn't interact with light, doesn't scatter or absorb. It's there only through gravity, shaping everything from galaxies to the large-scale structure of the cosmos. Without it, the universe would never have formed stars at all. In a sense, galaxies like Dragonfly 44 are pure expressions of that invisible architecture, the skeleton of the universe laid bare. If you could somehow fly through it, you wouldn't see a thing. The few lonely stars would drift in near-perfect darkness, separated by unimaginable gulfs. No glowing nebulae, no golden cores, just emptiness shaped by unseen hands. It's haunting and beautiful in its simplicity. A galaxy without light, made entirely of what we cannot touch or know. The universe has many faces, some radiant, some silent. Dragonfly 44 is the latter, a reminder that most of existence hides in shadow, and that sometimes, the most powerful things are the ones we can't see at all. The planet where it snows metal. If you think weather on Earth is wild, hurricanes, lightning, and polar ice, the universe offers storms that make ours look like whispers. There are planets where it rains glass, where lightning stretches thousands of kilometers, and even worlds where it snows metal. One such place orbits a star called WASP 121, about 850 light-years away. The planet's name is WASP 121b, and it's one of the most extreme, hot Jupiters ever discovered. This world is so close to its parent star that it completes an orbit every 1.3 Earth days. Its dayside temperature exceeds 2,500 degrees Celsius, hot enough to vaporize metals like iron and magnesium. The atmosphere literally boils, and the metal vapors rise into the upper layers like steam. But as those vapors drift toward the cooler night side, they condense and fall back down, not as rain, but as metallic snow. Picture that. Iron droplets solidifying midair, drifting down in shimmering flakes across a horizon lit by a white-blue sun. It's not snow as we know it, it's a storm of glittering metal dust, frozen by the cold shadow of space. The temperature difference between the two sides of WASP 121b is staggering, about 1,000 degrees. The planet is tidally locked, meaning one hemisphere always faces the star, burning in eternal day, while the other remains shrouded in perpetual night. At the border between the two, the terminator zone, immense winds whip metal vapor from hot to cold at supersonic speeds. The atmosphere churns like a furnace in reverse, boiling on one side, freezing on the other. The Hubble and James Webb telescopes have both studied this world in detail, using spectroscopy to map its temperature, chemistry, and circulation. They found water vapor, iron, magnesium, and even traces of vanadium, all interacting in a metallic haze that defies ordinary physics. The upper atmosphere glows faintly purple-blue from the intense radiation of its nearby star. Underneath, the gases shift and mix, creating currents so violent that they may strip material away entirely. Some of that vapor escapes into space, forming a comet-like tail of glowing gas trailing behind the planet. In time, WASP 121b may lose much of its mass, slowly evaporated by its own star. But for now, it's a spectacle of thermodynamics pushed to its limit, a world that burns and freezes at once. And the metallic snow isn't the only surreal part. Deep below the clouds, where pressure and heat mix, scientists believe iron could rain downward as liquid, pooling into a superheated ocean of molten metal thousands of kilometers wide. It's a planet that literally bleeds iron. We sometimes call these worlds impossible planets, because by all our old assumptions, gas giants shouldn't survive this close to their stars. Their atmospheres should have been stripped away long ago. But nature is stubborn, it always finds balance in chaos. WASP 121b stands as proof that the universe has no respect for limits. It stretches every variable, heat, gravity, pressure, chemistry, to the edge, and somehow it works. If you could somehow stand in that alien sky, protected by a miracle of engineering, you'd see a star so close it fills half the heavens. The horizon would glow white, winds would scream like jets, and from above, molten iron flakes would drift down in a fiery metallic snowfall. A storm so alien it would look like art, dazzling, lethal, and impossibly beautiful. This is what makes astronomy humbling. Every discovery widens the definition of possible. Some planets glow with diamonds, some rain glass, and others, like this one, snow in steel and fire. It's as if the cosmos keeps rewriting its own poetry, one impossible world at a time. The planet that shouldn't exist. Some discoveries in astronomy make scientists excited. Others make them uneasy. And then there are the ones that make them say, this can't be real. That was the reaction when astronomers found a planet that shouldn't exist, a world orbiting so close to its star, and yet so massive, that by every model of planetary formation, it simply shouldn't have been possible. Its name is TOI 849b, and it sits about 730 light-years away, orbiting a star much like our Sun. On paper, it's about 3 times the size of Earth, but it weighs more than 40 times as much, denser than any known gas giant, and far heavier than a rocky planet should be. It orbits its star every 18 hours, so close that its year lasts less than a single Earth day. The heat there exceeds 1,500 degrees Celsius, hot enough to melt iron and vaporize rock. So what is this thing? At first, scientists thought it must be a super Neptune, a bloated gas world stripped bare by its star's radiation. But the numbers didn't fit. The atmosphere was too thin, the mass too high, the composition too strange. Then came the astonishing conclusion, TOI 849b might be the naked core of a former gas giant, the exposed heart of a planet that once looked like Jupiter. In other words, this is a planet's skeleton. At some point in its history, TOI 849b may have formed far from its star with a massive envelope of hydrogen and helium. But then, catastrophe struck. Perhaps it migrated inward, where stellar winds tore its atmosphere away. Or maybe a collision with another planet blasted off its outer layers, leaving only the heavy metallic core behind. Whatever happened, what remains today is a world of compressed rock and metal, an exposed planetary heart orbiting in blistering heat. It sits in what astronomers call the Neptune Desert, a region around stars where planets of this size shouldn't exist at all. In this range, small rocky worlds can survive, and giant gas planets can exist farther out, but something this dense and this large is completely out of place. It's a world that defies categories, neither Neptune nor Earth, neither gas nor rock. If you could somehow stand on its surface, you couldn't, but imagine, the gravity would be 10 times stronger than Earth's. The sky would glow white-hot from the nearby sun, and the horizon would shimmer with vaporized minerals, raining molten rock. TOI 849b shouldn't exist. And yet, there it is, a fossil of a world that used to be, a stripped-down relic of planetary evolution, orbiting too close, shining too fiercely, surviving long after logic says it should have died. That's the recurring theme of the cosmos, isn't it? What shouldn't be, somehow is. The universe writes stories that begin with impossibility, and then it proves them true. The star that erased its own past. Every star has a story. They're born, they live, they die, and the light they emit carries the record of that journey. The elements in their spectra tell us what they've burned, what they've created, what they've lost. But once in a while, astronomers find a star whose light tells no story at all, as if it has erased its own history. One of those stars is called LP 40-365, sometimes nicknamed the anomaly star. It doesn't fit any known category. It's too fast, too light, and chemically too strange. This star is what remains after a partial supernova, an explosion that failed to finish the job. Here's how that works. Usually, when a white dwarf accumulates too much material from a companion star, it reaches a critical mass and explodes completely, leaving nothing behind. But sometimes, the explosion doesn't go all the way. The outer layers detonate, but the core survives, scarred, burned, and hurled away at incredible speed. LP 40-365 is one of those survivors. It's racing through our galaxy at 850 km per second, fast enough to escape the Milky Way entirely. That's how we know it's a runaway star, the remnant of a supernova that didn't quite finish dying. Its light reveals bizarre chemistry, no hydrogen or helium, but an abundance of iron, magnesium, oxygen, and nickel, the ashes of nuclear fusion. Its spectrum is the signature of something halfway between life and death. In effect, LP 40-365 forgot what kind of star it was. It doesn't burn anymore, yet it still glows faintly from residual heat. It doesn't orbit anything, yet it carries the momentum of an ancient catastrophe. It's both corpse and survivor, a celestial paradox. What's more, its interior may still contain unburned material from before the explosion, mixed chaotically with the debris of fusion. It's a kind of cosmic palimpsest, an object whose original structure was overwritten by fire, but not destroyed entirely. When scientists model its origin, they suspect it once had a binary partner, two white dwarfs spiraling together. One exploded first, partially igniting the other. The blast separated them, sending LP 40-365 careening through the galaxy like shrapnel. It's traveling so fast that in a few million years, it will leave the Milky Way completely, heading into intergalactic space, a lonely ember drifting forever through darkness. Its motion tells a story of unimaginable violence, but its composition tells none. It's a star with its memory burned away, stripped of hydrogen, stripped of history, stripped of identity. We often think of stars as eternal, fixed points in a sea of time. But LP 40-365 is a reminder that even stars can lose themselves. That even something born in light can forget where it came from. If the universe has ghosts, this is one of them, a stellar phantom racing toward infinity, carrying no record of its birth, only the speed of its escape. And someday, long after it fades from view, its journey will still continue, silent, directionless, and endless. A star without a past, falling forever into the future. The planet that orbits a dead star. Planets aren't supposed to survive their suns. When a star dies, it doesn't go quietly, it expands into a giant, devours everything nearby, then collapses in on itself, leaving behind either a white dwarf, a neutron star, or, if it's massive enough, a black hole. That's the end of the story, or so astronomers thought. Then they found a planet that didn't get the memo. Roughly 2,600 light-years away, in the constellation Lyra, circles a world known as PSR B 1620-26b, nicknamed the Methuselah planet. It's about 12.7 billion years old, almost as old as the galaxy itself, and it orbits something that shouldn't even host planets anymore, a pair of dead stars. At the system's center are two corpses of suns, a white dwarf and a pulsar, locked together in a tight orbit. Around them both, this ancient planet traces a vast, stable path roughly twice the distance between Earth and the Sun. The pulsar, a rapidly spinning neutron star, flashes beams of radio waves with clock-like precision, hundreds of times per second. Those pulses are what gave away the planet's existence. As the planet orbits, its gravity slightly tugs the pulsar, altering the timing of the radio beats. Those tiny variations told scientists something astonishing: there was a planet circling this stellar graveyard. That shouldn't be possible. When the original stars died, their explosions or expansions should have obliterated anything nearby. The gravitational chaos alone should have flung every planet away. So how is PSR B 1620-26b still here? The leading theory is that it moved in afterward. This whole system lives inside a globular cluster, a dense ball of ancient stars called M4. Stars in such clusters often swap partners through gravitational encounters. At some point billions of years ago, the pulsar white dwarf pair may have captured the planet from another star that passed too close. That would make Methuselah a true wanderer, a world stolen and adopted by a pair of dead suns. And because globular clusters are among the oldest structures in the universe, that means this planet has existed almost since the dawn of time. It formed before the Earth, before our Sun, before the Milky Way finished assembling itself. If there were ever life there, improbable, but imaginable, it would have watched galaxies collide, stars live and die, and still be orbiting now, ancient beyond comprehension. It's proof that even in cosmic death, stability can emerge. The pulsar ticks, the white dwarf glows faintly, and around them both, a planet older than Earth by billions of years continues its endless circuit, a survivor orbiting a pair of ghosts. The galaxy colliding with ours. Look up at the Milky Way on a clear night, a pale river of starlight flowing across the dark. It feels eternal, untouchable. But it's not. Our galaxy is moving, and it's heading straight for another. Far across the void, the Andromeda Galaxy, M31, drifts toward us at 110 km per second, pulled by mutual gravity. It lies about 2.5 million light-years away, close enough that its light can be seen with the naked eye. When you glimpse that faint smudge in the sky, you're looking at our future. In roughly 4 billion years, the Milky Way and Andromeda will collide. It won't be an explosion. Galaxies are mostly empty space. When they merge, stars rarely crash into one another. Instead, gravity reshapes everything, spiral arms twist into tidal streams, black holes spiral together, and vast clouds of gas compress into brilliant bursts of star formation. From far away, it will look like a slow-motion dance, two luminous spirals weaving into one, their shapes distorting over hundreds of millions of years until they fuse into a single, elliptical supergalaxy sometimes called Milkomeda. Our own solar system will probably survive the collision physically intact, but its sky will never look the same. Imagine this. As the merger begins, Andromeda will swell across the heavens, growing brighter each night until it dominates the sky, a second Milky Way overhead. The arcs of both galaxies will stretch and interlace, turning the night into a canvas of light and motion. Over millions of years, the two galactic cores will drift closer, orbiting one another like twin suns until their central black holes finally merge. That event will unleash gravitational waves powerful enough to ripple spacetime across the cosmos. To any future beings alive to witness it, the view would be beyond words, the entire sky ablaze with intertwined galaxies. And when the chaos settles, the new galaxy will be calmer, rounder, and redder, its star-forming gas spent in the frenzy of collision. The Sun, by then near the end of its life, may orbit quietly on the outskirts of this merged world, or be flung outward into the halo, carrying the remnants of the solar system into intergalactic night. Astronomers have simulated the event countless times, and the result is always the same: destruction and rebirth. The Milky Way and Andromeda aren't enemies, they're destined partners. This is how galaxies evolve, by merging, mixing, and creating something new. In fact, the entire local group, including dozens of dwarf galaxies, will eventually follow. Over trillions of years, everything nearby will merge into one massive island of stars drifting through expanding space, surrounded by silence. So when you see that faint blur of Andromeda shining on a cold night, remember, that's not just another galaxy. That's our future home, rushing toward us. The sky we know is temporary. But the beauty of its transformation will be unimaginable. The black hole that wanders the galaxy. Most black holes sit still. They lurk in the hearts of galaxies or sleep where a massive star once was, invisible, patient, eternal. But not all of them stay put. Some move. Some drift through the galaxy like cosmic predators, unseen and unstoppable. Astronomers call them rogue black holes, and they're not just rare curiosities, they might be everywhere. The Milky Way alone could contain hundreds of millions of them, each the ghost of a dead star, each silently gliding through space. Most are small, a few times the mass of the Sun, but their gravity is absolute. They travel alone, leaving no light, no trace, except for what they distort around them. In 2022, scientists detected one for the first time. It lies about 5,000 light-years away, in the direction of the constellation Sagittarius. And though it's completely invisible, we know it's there, because we caught it bending starlight. As the black hole passed in front of a background star, its gravity warped the light in a process called gravitational microlensing. The starlight curved, brightened, and shifted for weeks, then faded as the invisible object moved on. By measuring the distortion, astronomers calculated its mass and speed, about 7 times that of the Sun, moving through space at 160,000 kilometers per hour. It's not orbiting anything. It's not bound to a system. It's just wandering. How does a black hole end up adrift? The answer lies in the death of massive stars. When a supernova explodes asymmetrically, the blast can give the newborn black hole a powerful kick, a recoil that sends it hurtling away from its birthplace. Over billions of years, those exiles travel through the galaxy like ghosts, bending the fabric of space wherever they go. Most of them are invisible forever. Unless they pass close to gas or dust, there's nothing for them to feed on, no light, no sound, no warning. A rogue black hole could drift silently past our solar system and we'd only know when our orbits began to twist. And yet, even in their invisibility, they sculpt the galaxy. Their gravity shapes stellar clusters, tugs at star streams, and may even seed new star formation by disturbing the interstellar medium. They are destruction and creation, both at once. If you could see one, truly see it, you'd find no surface, no color, no line between space and abyss. Just a shadow, where the geometry of the universe folds in on itself. Around it would be the faint shimmer of distorted starlight, a halo of the world behind it bent into a ring, an Einstein ring, named for the man who first predicted that even light can be caged by gravity. Inside that ring is silence. Not a metaphorical silence, literal, perfect silence. Because inside the event horizon, not even sound waves can form. Time itself slows, then stops. And yet, the black hole keeps moving. Through the galaxy, through the dark, through the scattered arms of starlight, a drifting scar of gravity, erasing and reshaping as it goes. It is the closest thing to eternity we know. And it will outlast everything else. The end of time itself. We talk about the end of the universe as though it's something we'll witness, an event like a sunset or a final page. But the truth is more unsettling, the end isn't a single moment. It's a long, slow fade into silence. To understand how it ends, we have to stretch our imagination across trillions upon trillions of years, past the death of the sun, past the fading of the galaxies, past even the decay of matter itself. Here's how physicists see the future unfolding. 1. The stellar era. Right now, we live in the age of stars, bright, brief, and fiery. But this era won't last forever. In about 10 trillion years, the last stars will burn out. Red dwarfs, the most efficient of them all, will glow faintly for eons, then cool into dark embers called black dwarfs, the same destiny awaiting our sun. The night sky will go black as the stars wink out one by one. 2. The degenerate era. When the stars are gone, only the leftovers remain, white dwarfs, neutron stars, and black holes. They'll drift quietly in the dark, occasionally colliding, merging, or being swallowed by gravity wells. Planets will freeze. Orbits will decay. Galaxies will unravel, their remnants scattered like ashes across expanding space. The universe will become a graveyard of cold remnants and wandering black holes. 3. The black hole era. As time stretches into unthinkable spans, 10 superscript 1 years and beyond, black holes themselves will begin to fade. Hawking radiation, the slow quantum leak predicted by Stephen Hawking, will cause them to evaporate particle by particle. One by one, even the greatest of them, the monsters that once ruled galaxies, will vanish in a final, faint whisper of light. No stars, no planets, no black holes. Just cold particles drifting in an ever-thinning fog. 4. The dark era. What's left after that is not darkness, but nothingness, a diffuse ocean of photons, electrons, and lonely atoms spread so far apart that interaction becomes impossible. No structure. No motion. No time, in any meaningful sense. Because time depends on change, on things happening. And when nothing happens anymore, when entropy reaches its final, still state, time itself stops having meaning. This is the heat death of the universe, not fire, but stasis. The end not with a bang, but with an eternal sigh. In that silence, no observer will exist to know it's ended. There will be no memory, no thought, no witness. Just the smooth, cold perfection of equilibrium. But here's the strange comfort, everything that exists now, every star, every planet, every fleeting moment of life and thought, is part of the process leading there. The universe is not dying against itself. It's completing itself. We are temporary, but we are also essential. For a brief instant, we are the way the universe sees its own beauty. And even when the light fades, that moment, the fact that it was, will always have been. Time's story may end, but the fact of its existence never can. The black holes will wander. The stars will fade. The galaxies will fall apart. And yet, in that infinite quiet, the memory of the cosmos, written into the structure of what once was, will remain, forever etched into the silence beyond time. The story of the universe isn't a straight line. It's a long, spiraling song, one that began in silence, built to a roar of fire, and is now slowly, patiently, drifting back toward quiet. Every discovery we've made, diamond stars, glass-raining worlds, galaxies of shadow, planets of fire, has been a single note in that melody. Each tells us that the cosmos is both violent and delicate, brutal and astonishingly gentle. When we look outward, we are also looking backward. Every photon that reaches our eyes is ancient history, light that began its journey before humans had names for the sky. We stand on a small world, wrapped in thin air, and catch these messages as they fall. They whisper of stars that lived, burned, and died before our atoms ever learned to think. In the end, the universe is not a place, it's a process. Creation and destruction are the same motion seen from opposite sides. The death of a star becomes the birth of worlds. The collapse of matter becomes the seed of new galaxies. Even the black holes, those hungry hearts of darkness, are sculptors, shaping the geometry of space, recycling energy into forms we have yet to imagine. Our own planet is proof of that cycle. Every rock, every ocean, every breath is made from the ashes of stars. We are, quite literally, the dust of explosions that happened billions of years ago, arranged by chance and chemistry into a pattern that can ask, why? When you trace that line far enough, it leads not just to the beginning of time but to the question of awareness itself. Somewhere in the slow cooling of the cosmos, matter became capable of wondering what it was. Out of hydrogen, curiosity appeared. Out of gravity, hope. Maybe that's the universe's trick. It builds observers to watch itself fade, so that, for a brief moment, its beauty is known. The black holes will wander, the galaxies will collide, the last light will drift away. But the act of having seen it, of having measured, written, imagined, means that the universe has already succeeded in being understood. That understanding is not erased by darkness. It becomes the darkness, knowledge suspended in entropy, memory woven into the background of existence. And so the story doesn't really end. Even when every particle stops moving, the pattern that was, the stars, the storms, the questions, will still be written into the structure of spacetime, frozen but eternal. The universe is not gone, it is complete. If you could stand outside time and look back, you would see everything at once, the first spark, the last photon, every heartbeat in between. It would look like a single flash of light, unfolding forever. That flash is us. The galaxies, the atoms, the people who looked up and wondered. We are the moment the universe became aware that it exists. And that, perhaps, was the reason for all of it.